So valence electrons is the number on top, and we said when we have ions, we're going to either add or remove electrons. And the reason I'm going over this again is because we're actually going to be drawing the structures today, so I want this to be really fresh in your mind. We said that we're going to follow the patterns in our chart. We're going to count our octets and duets. And remember, when we're counting, the dashes equal 2 electrons. So each dash is equal to 2 electrons. So maybe I'll just write dash equals 2 electrons. And those 2 electrons in every dash count for each of the atoms. And then we're going to check what are called the formal charges, and that's what this page of notes will be that we do today. And the goal for everything is going to be octets, except for H, which has a duet because that's all it can do for its s orbital. And we said that carbon is always going to make 4 bonds and have no lone pairs. Nitrogen has 3 bonds and 1 lone pair. Oxygen has 2 bonds and 2 lone pairs. The halogens make 1 bond and have 3 lone pairs. Hydrogen, 1 bond, no lone pairs, and boron is a weirdo, and it does not follow the octet rule. So then, what we were going to talk about today was the formal charge. And the point of formal charge is it basically gives us a way to look at our Lewis structure and say, did we do our best job to write this Lewis structure, and is there any other way that we can maybe make it better? And so this is used to help check our Lewis structure, because what I will always ask you for is the best Lewis structure. So there are ways to draw molecules that might seem correct, but are maybe not the best possible version, because we can make it better by improving the formal charges. And so the definition of formal charge is a calculated charge ignoring the effects of electronegativity. So we don't care which one's more electronegative, we just care what's happening within the molecule. So the definition of formal charge is the number of valence electrons, and so we get this from the periodic table, minus the number of non-bonding electrons. So we're counting those individually, not as pairs, plus half of the number of bonding electrons. Okay, so this is kind of a very long definition, and this is the formal definition. And then I get sick of writing this whole thing, this large quantity every time. So I'm going to replace it with a shortcut that I'll show you. But for the first while, we're going to do both just until you get comfortable with one or the other. So the shortcut version is where we do valence electrons, so that stays the same, minus number of things touching it. And so this can either be a dot or a dash, and they count equally. Okay, so that's just how we write out the formula for it. But basically, let's talk about what we're trying to do with formal charge. So with formal charge, our goal is always to try to make it so that, if at all possible, we will have 0 formal charges, because 0 essentially means stable or happy, okay? So we are going to try to do zeros on every atom if it's possible. So what that means is we are going to follow the patterns from the previous page and try to make them stable by both having the octet rule and following the patterns. So if you have to have charges, because there's no other way to draw the molecule, then we have to think about electronegativity. So we would want a negative charge Do we want that on the element that's more electronegative or less electronegative? Which one would want to have a negative charge on it? More, right? The one that's more electronegative is more likely to be negative. So on the more electronegative atom. Or if we have to have a positive charge, then what do we want that to be on? Which one? The more or the less electronegative atom? Less, right? Makes sense. Come on, you can write. All right. Then, if your molecule is neutral, just like when we were finding oxidation numbers back in the day, what do our charges have to add up to if our molecule is neutral? 0, yeah. So if you have a neutral molecule, then our formal charges must add up to 0. But if we have an ion, then what should our charges add up to? Whatever the charge is on the ion, right? That makes sense. So if we have an ion, then the formal charges must add up to the overall ion charge. Okay, let's look at a quick example. So we're going to draw the Lewis structure for HF, and what we're going to do is we're going to follow our rules for HF. So H makes one bond, no lone pairs. Fluorine also will make one bond, but it's going to have 3 lone pairs. Okay? So let's start by counting our valence electrons. So when we count our valence electrons, we always do that first. Hydrogen has 1 valence electron. Look at your periodic table. You can see it's in column 1. And fluorine has 7 valence electrons, so we have a total of 8 electrons. And then we're going to follow the pattern. So we're going to write H, and we're going to write F. Both of them are going to have 1 bond. So they're going to share a bond. And we have 2 electrons in that dash, meaning we have 6 more to put in. Where are we going to put the rest of the electrons? On which atom? Fluorine, yeah. So 2, 4, 6. All right, let's check if we have octets. So fluorine has 2, 4, 6, 8. Good. We're happy with that. And hydrogen has 2. Happy with that. All right, so good. We followed all of our rules. So now our next job is to check our formal charges. So when we do formal charge, let's start by following the formula we just learned. So formal charge, the definition says the number of valence electrons. So we know for hydrogen, that number is 1. Okay, now let's look at the rest of it. The number of non-bonding electrons. So that means lone pair electrons. Does hydrogen have any of those? No. So we'll put a 0. And then plus 1/2 of the number of bonding electrons. How many electrons are in this bond here? 2, okay? So we'll put 2 in parentheses. What is 1 minus 1/2 of 2? 0. So we're good with that. Let's put a little check because we're happy with that. Okay, now let's do the same thing for fluorine. How many valence electrons does fluorine have? 7, okay. How many non-bonding electrons does fluorine have? 6, yeah. 1, damn it, that's the eraser. 1, 2, 3, 4, 5, 6. Okay, plus half of the number that are in the bond. How many are in the bond? 2. Okay, so what does that equal? 0, just like we wanted, right? And then when we add these up, we get 0, so we're happy about that. And if you want to do the shortcut, this is where we just look at the number of valence electrons. So the first number we write down is the same. But now, instead of treating the non-bonding and the bonding separately, all we're going to do is count how many things are touching it. So for hydrogen, we just have 1 dash touching it, so we're going to say 1. And for fluorine, we have 1 dash, 1, 2, 3, 4, 5, 6 dots, so that's 7 things touching it, for a total of 0. Okay, so fluorine still has an octet, because when we're counting for the octet rule, we still have 8 things, or 8 electrons surrounding fluorine. But for checking the formal charge, since we count half of the number in the bonding electrons, that's why we get 7 instead. Okay, you've heard enough out of me. What I'd like to do is in your groups, I would like you to do, let's say A through D. Looks like we have some good progress, so let's discuss what we did here. Okay, Carly, why don't you start us off on CH4? So we know that we have 8 electrons, and which one did we put in the middle?
We put carbon in the middle.
Why?
Because it has 4 valence electrons and there's 4 hydrogen bonds that need to be made.
Yeah, so we usually, a really nice rule is you're going to put the one in the middle that you have the fewest of. Generally, we say that also the less electronegative atom goes in the middle, but that doesn't always work out, so it's easy to just say the one we have fewest of, that one goes in the middle. And how many bonds does carbon like to make? 4. So that's convenient because we have 4 hydrogens, so it can make 1 bond to each hydrogen. Aha. Okay. We have an Lexi. Do we have 8 electrons in this molecule? Yeah, because each dash is 2 electrons. Does carbon have an octet? Yes. Yes, because the 4 dashes represents 8 electrons, and hydrogen only needs a duet. So let's do formal charges for our molecules. So carbon, how many valence electrons does it have, Lexi? And how many, let's do the long version just real quick. How many are non-bonding electrons? 0, yeah. And how many are in the bond? Well, there's actually 8, yep. So that's how we get 0 here. But if you did the short version, which I think a lot of you did, then you just went like that, which is the same exact thing. All right, now we're going to do the same thing for hydrogen. Lily, how many valence electrons?
1.
Okay, and how many are non-bonding?
0.
And how many are in the bond?
1.
2, that's right. So yeah, this is a little bit longer, and then if we shortcut it, you're right that one thing is touching hydrogen, so we're good there. And then we have to make sure that we multiply this by 4, because there are 4 of them, for a total of 0, just like we wanted, right? So you have to account for the number of each of the atoms that you have, if they all have the same formal charge. And if they don't have the same formal charge, like if they have different bonding, which we haven't encountered yet, but we will, then you have to do them separately. Okay, let's look at ammonia. So which element did we put in the middle for ammonia? Willow. N, yeah, that's right. Okay, and how many bonds does nitrogen like to make? 3. Okay, good. And how many lone pairs does it like to have? Okay, so we drew this structure just based on our patterns. Okay, does nitrogen have an octet, Max? Yes. So 2, 4, 6, 8 electrons around nitrogen. Octet. And we used up the 8 electrons that were valence. Okay, and we know hydrogen has a duet, so everybody's happy. All right, let's do some formal charges. So nitrogen, how many valence electrons, Max? 5, yes. How many of those electrons are non-bonding? 2. And how many are bonding? 2, 4, 6. So it's 6. Yeah, sorry. Okay, we probably won't do this definition because it feels like it's more confusing than helpful. Okay, so we get 0 here. So remember, the shortcut is 5 minus 1, 2, 3, 4, 5. So we still have an octet, right? Octets is where we count the dashes as 2. But for formal, we can count the dash as 1 instead of doing this whole thing. Okay, so let's also do our counting for hydrogen. How many valence electrons does hydrogen have, Izzy? 1. And how many are non-bonding? 0. And how many are in the bond? 2. Okay, so that's the 0. Our shortcut is a lot quicker. One thing touching it. Then we have to multiply this by 3, and it works out to 0. So we're happy campers. Well done. Okay, let's go on to OF2. So for OF2, Drake, which one did you put in the middle? O, okay. And how many bonds does O like to make? 2. All right. Did you make 2 single or a double bond? 2 single. Okay, 1 to each fluorine. So we've used up 4 of our 20 electrons. Where should I put the rest?
2 on top and 2 on bottom of the row.
Okay.
And then 6 around each floor.
Okay, excellent. So if we count our electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that's how we got 20 electrons. Then we have to decide, do we have octets everywhere? So fluorine has 2, 4, 6, 8 electrons. Oxygen has 2, 4, 6, 8 electrons. And our other fluorine has 2, 4, 6, 8 electrons. So we've got our octets, we've counted our electrons, everything's good. So let's draw our molecule real quick again so it doesn't look crazy. All right, and we're going to do our formal charges, okay? Both of our fluorine atoms have the same bonding, so we can just do the formal charge once and double it. Or if you want, you can do the 2 separately. It's up to you. But I think everybody's cool with the idea that if they're the same, we can just double them, right? Yeah, the bonds are the same, so the formal charges will be the same. We're good with that? Okay. So we'll just do our shortcut method. All right, so for O, how many valence electrons does O have, Drake?
6.
And how many things are touching oxygen? 6. Okay, perfect. And for fluorine, we have how many valence electrons?
7.
And how many things are touching it?
7.
All right, so this molecule is a happy molecule, and we're good. All right, let's move on to CO2. Evan, how many bonds does carbon like to make?
4.
4. How do we make that work when we only have 2 oxygens?
We can do a double bond with each oxygen.
Excellent. We can do double bonds to each oxygen. And guess what? That makes oxygen happy too, because oxygen likes to make 2 bonds. It doesn't matter if they're 2 single or 1 double. We made it happy with the 2 bonds that it wanted. So how many electrons have we used up right now?
Just 8.
Just 8, right? So we've got 2, 4, 6, 8. And how many electrons should we put in?
Well, you should have like 4 for each oxygen.
That's right, because we need a total of 16. We've used 8, we need 8 more. 2, 4, 6, 8. Does everything have an octet? Yes, we do. Let's show the octets. Here we go. 2, 4, 6, 8. 2, 4, 6, 8. Then for carbon, 2, 4, 6, 8. All right, we've got our octets in place, so that is a good Lewis structure. That's also why carbon dioxide is a pretty stable molecule. All right, let's look at some formal charges. Okay, Evan, for oxygen, how many valence electrons?
6.
How many things touching oxygen?
6.
Okay, and carbon?
That'd be 4 and 3.
4 and 4. Excellent, and we would just double this one for a total of 0. Good. All right, now let's look at SeOF2 and NO2 minus. The first thing that we always do is we're going to count our valence electrons. So let's get started on counting valence electrons. So selenium has 6. It's in the same column as oxygen. Oxygen has 6. And fluorine has 7. There are 2 of those for a total of 26. Yeah? Okay, I'm bad at mental math, so. All right, so propose to me what an idea that you had during your brainstorming. Okay? So somebody tell me how you wanted to arrange these atoms based on following the patterns. Okay, no one's gonna do it until I call it. You guys, what did you think you wanted to do?
I just followed the chart.
Okay, and tell me how you bonded your elements. How did you draw it?
I had, S, C, and O with a bond,
Okay,
and then I had to the right, and then I put the bond with fluorine,
okay.
and then I had all
The lone pair is filled in. Okay. So if we do it this way, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. Oxygen has 2 bonds and 2 lone pairs. Fluorine has 1 bond and 3 lone pairs. And selenium, which is in the same column as oxygen, so it should be similar, also has 2 bonds and 2 lone pairs. So let's calculate our formal charges. And I should also add that everything has an octet, which is also nice. So for selenium, Kendra, how many valence electrons?
6.
And how many things are touching it?
Oh, I
That's okay. 1, 2, 3, 4, 5, 6. Okay. Oxygen, how many valence electrons? Okay. And 1, 2, 3, 4, 5, 6 things touching it. And then we've got our fluorine. How many valence electrons? 7. Okay. And we've got 1, 2, 3, 4, 5, 6, 7 things touching it. All right. So I'm pretty happy with this structure. I saw a couple of these. Did anybody have anything different? I know some of you did. Just tell me what, be honest. Come on. Go ahead,
We
Chase.
had something different.
Tell me about what you had.
We threw cesium in the middle.
Selenium, yes. Excellent. And then what did you do?
Then we put the fluorine on the outside, and then we double bonded the oxygen.
Okay. So 2, 4, 6, 8 electrons. Okay. And then you put some lone pairs on it.
Yes.
Okay. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. How'd we get 26?
Well, we know it's wrong, but like, we now know it's wrong. That's just
Oh.
what we did.
Yeah, but did you put 26 electrons in?
I'm not sure, I already erased it.
Oh.
I think so.
Okay, so I actually like this structure because it does follow the rules for oxygen and fluorine, and you would have formal charges of 0 on all your elements, but you would need 26 electrons, which you would put there, and then you would have formal charge of 0, but this breaks the octet rule, and I haven't yet said that that's allowed, so we're gonna not. But there's a reason why there's a best Lewis structure based on formal charge and following the octet rule and counting valence electrons that we usually draw. And that's why there could be multiple possibilities. But if you factor in all the things you want to do, the rules we want to follow, it leads you to the best possible version of it. Am I right? Okay, so I will say to you that this was a good choice, what you did here. This followed the rules and made sense, but we broke the octet rule, so we could see that it wasn't the best. But if and when we're allowed to break the octet rule, it's also an option. All right, let's talk about the nitrite molecule. So the first thing we do is we count our valence electrons. So nitrogen has 5, oxygen has 6, and there are 2 of them, and we had that -1 charge, and the -1 charge adds 1 more electron. So we have a total of 18 electrons. All right, so how did we place the atoms in this molecule? So which one did we put in the middle? Carly, which one did you put in the middle?
Nitrogen.
Okay, and what kind of bonding did you do to each of the oxygen atoms? Did you do single bonds, double bonds?
Double.
Okay, let's start there, because if we follow the rules, this is tricky, because according to our rules, how many bonds does nitrogen usually make, Lexi? Oh, I was just pointing at you. I wasn't giving you the answer. According to our patterns, 3, but now we have 4. But oxygen usually makes how many bonds according to our rules, Lexi? 2. So we can't really follow the rules for all of them in this scenario. So what do? What did you guys do, Lily?
That's what we did.
That's what you did. Okay, well, let's go for it. So if we've got 2, 4, 6, 8 electrons, we've got to get to 18 by giving octets. So 8, 10, 12, 14, 16, 18. What's the problem with this structure, Lily?
The nitrogen's not an octet.
That's right, nitrogen's not an octet. So we can't really do this. So this has more than an octet on nitrogen, so we can't make it work. Okay? But drawing it is still good because it helped you see that. All right, Willow, what did we do instead? Keep nitrogen in the middle. Okay? Okay, so now we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? Does everything follow the octet rule? Willow? Oh, it doesn't follow its pattern, but does it have an octet? Does it have 8 electrons? Yes, it does. Okay, also, when we draw ions, we have to include brackets and a charge to show that we're not lying about how many electrons we have. So when we draw our molecule, we have to draw brackets and the charge around it. All right? So we have octets, we have the right number of electrons. Now the final test is the formal charges. Okay, but in this case, are the oxygens the same, Max? No. Why? That's exactly right. So we're going to label this as A, and we're going to label this one as B. Or we could label them left and right. Maybe that's easier. Okay, we'll do the one on the left and the one on the right. Okay, so left Or actually, let's be smarter and just do double and single. Why am I having such a hard time today? So oxygen with the double bond, D means double, okay? So this one does follow the rules. We have 6 valence electrons. And Max, how many things is this oxygen with the double bond touching? 6. 1, 2, 3, 4, 5, 6. Okay, good. All right. Tell me about nitrogen, Max. How many valence electrons?
5.
And how many things touching it? 5. Good. All right. Now, Izzy, talk to me about oxygen with the single bond. How many valence electrons? 6, but now how many things are touching it? 7. 1, 2, 3, 4, 5, 6, 7. Aha. So what does this equal? -1. Does it make sense that the -1 is on oxygen instead of nitrogen? Why? It's more electronegative. Very good. Yes. Does the overall charge match of the formal charges match the charge on the ion? Yes, it does. It adds up to -1. Aha. That's how we did it. So, tomorrow, we're going to talk about why we put the double bond on the left and whether it actually matters whether we did that. Okay? That's it. So tomorrow it's going to get exciting when we talk about resonance. Ah. Okay, good job, everybody.